All right. Hello and welcome, everyone. We're so glad that you could be joining us today. My name is Stephanie, and I am the Multimedia Communications Specialist here at Posit Science, and I'm going to be your co-host for today. This webinar is one of many webinars that are a part of our larger BrainHQ Academy series, and today's topic is the different facets of memory. Let's go ahead and look to the agenda. So after the agenda, we are going to go ahead and roll a couple of polls for you guys. When those polls come up, you can go ahead and select your answers and submit them, and then we will share those results with everyone once the poll has concluded. Then Dr. Mouna Attarha is going to give a presentation about memory. Mouna, you want to say hi?
Hi, everybody. It's great to be here and to talk to you about the different kinds of memory that we have.
Yeah. So Dr. Attarha is a repeat presenter here within the webinar series. For those of you who have not seen her before, she earned her PhD in cognitive science and has been a senior scientist at Posit Science since 2016. She leads NIH-funded clinical trials investigating the neurochemical changes that occur by training with BrainHQ, and manages several trials looking at how BrainHQ exercises improves cognitive performance. Then after the presentation, we are going to be joined in discussion by our one and only Dr. Michael Merzenich. Hey, Mike, how you doing?
I'm doing good. Fun to be here.
Glad to have you, Mike. Mike is also a repeat guest here on the webinar series. But for those of you who are joining us for the first time, Dr. Merzenich is the co-founder of Posit Science and the brain behind BrainHQ. For nearly 5 decades, he has been a leading pioneer in brain plasticity and has published more than 150 articles in leading peer-reviewed journals. So very, very happy to have you both working on this webinar today.
Nice to be with you.
Yeah. Following that, we are going to have a live Q&A session. So throughout the presentation, if you have any questions about what's being presented, feel free to select the Q&A option on the Zoom control panel, type in your question, and then we will do our best to go ahead and answer as many of those as we can during the Q&A portion towards the end of the webinar. Now, another thing that I wanted to note is that today's webinar is being recorded and it will get posted to our YouTube channel sometime next week. If you want a notification as soon as that video goes live, you can head to youtube.com/brainhq and subscribe there, and YouTube will automatically send you a notification whenever any of our videos are published. All right, so let's go ahead and jump into our first poll. So Mouna had a very, very clever poll that she wanted me to run, so let me go ahead and launch that. So today's webinar is about memory. So the first question that we want to ask is, on a scale from 1 to 5, how confident are you that you can remember something if you saw it 100 times? 1 being not at all confident, 2 slightly confident, 3 somewhat confident, 4 fairly confident, and 5 highly confident. So if you've seen something 100 times, how confident are you going to be able to remember the details of it? Going to give it another 5 seconds here for people to get in their answers at the last second here. All right, I'm going to go ahead and call it there. We've got 85% of our audience jumping in on that. So let's share the results. Mouna, what was your prediction for this first poll?
I think that we would imagine that most people would be saying that they're fairly to highly confident if they were able to see something 100 times. And look at that.
And look at that. Highly confident had the most votes and fairly confident just behind. So that all checks out. Hypothesis has been proven there. We had a couple of people saying not at all confident. It's very much a
it's a pretty skewed distribution right there.
Yes, exactly. That's exactly what I was looking for. Thank you. All right. So now that we've taken a look at that and you guys are feeling pretty confident, let's go ahead and go to the next slide and open up the next poll. So for those of you that have seen things more than 100 times and can recall the details, this is really more for our American audience here. Which of the pennies here is the real penny? All of them have slight differences in them. Which one is the correctly formatted penny here? Oh, this is a very, very interesting distribution that I'm seeing now. All right, Mouna, what's your prediction for this poll?
So the chances of recognizing the real penny here is about 17% or 1 out of 6. So what I'm expecting to see is more a flat rectangular distribution where the responses are falling maybe around chance, an equal number of people selecting each of the 6 options.
All right. And Mike,
But we'll see.
Yeah, Mike, did you have a guess which of these pennies is the correct penny?
I guess 3.
You guess 3? Okay.
Probably wrong, but that's my guess.
Well,
Sure,
Mike,
sure.
you're telling that yes.
All right, so we have almost half of the people who answered the first question have answered the second question. So we're going to give us another 10 seconds or so before we end the poll. We don't want you running to your wallet or running to your change dish and looking at the pennies. We want to see if you can remember this.
Yeah, and I'm going to change my hypothesis to say now that 3 is going to be the lowest.
I think once people have submitted their answer, they can't change the answer. So people who locked in 3 before Mike had said it have to be committed to that answer. All right, so it looks like we have quite a few people have jumped in at the last second. So let's go ahead and end the poll there. Thank you everyone for participating. Let's take a look at these results.
We have a pretty smart audience here.
Yeah.
So 24% said penny number 1. 2 was the one that was least likely to be selected. Let's see, but it's pretty even across 1, 3, and 4, and a little less for 5 and 6. Okay.
Yeah.
Very exciting.
So there you go. Very interesting distribution there.
Yeah, more.
I will say 1 and 4 were the ones that I also got confused about. I also cheated and had to look up which was the correct penny. Yeah. 1 and 4. My prediction was that those were going to be the 2 top ones. So there we go.
So the correct answer is number 1. Number 1 is the real penny. You've likely seen a penny far more than 100 times in your life, but it's really hard to remember their exact details because we don't process them in a meaningful way. We usually take a quick glance and we stick them in our wallet, put them in our change jar. So the point of this demo is really to show that memory isn't about the amount of time you spend encountering an item. It's really the amount of time you spend paying attention to the details and encoding those details in a meaningful way that determines how well you can remember things. So memory isn't a passive process, it's an active process, and it actually requires some effort.
All right, and I think with that, Mouna, do you want to go ahead and take over the screen share and continue with the presentation?
All right, so let's talk about memory more broadly. Our brains are memory machines. Everywhere that people have gone looking to find different forms of memory, they've been able to find it. So it isn't that there is a specific location or a single hub within the brain responsible for all of memory. It's more that the whole brain itself is a memory center. And some would even argue that that's probably the brain's most significant achievement. Now, we can visualize the process of memory by taking a look at this overview of information flowing in through the senses and into the different facets of memory. And this process starts with some kind of sensory input into the brain. So that can include sensation from the body itself, but it most often, when we talk about external information, it's referring to the objects we see, the sounds we hear, the things we smell, the things we touch. And we have a bunch of architecture in the brain devoted to processing the information from these sensory centers. And where memory starts is where these sensory events stop. It's when we no longer see that phone number or hear that song or smell that smell or touch that object. Because what our brains want to do is to be able to grasp the important information, the important elements from the outside world, and then use that for adaptive behavior. So a simple division of the core types of memory that a lot of us think about are short-term memory storage, working memory, and long-term memory storage. And before we get to the fun stuff, I'm just kind of going to discuss some of these three core memory compartments. And then we'll be able to move on just for in terms of the terminology here. But short-term memory really just means being able to hold on to something for a few seconds without being able to do anything with it and without trying to remember it forever. So if you hear somebody's name, for example, and a few seconds later, some time passes, you still may have some kind of short-term memory trace of the name that you had just heard. But now if you look at the arrows on each of these boxes, you'll see that you can actually toggle across these different kinds of memory. So in order to go from short-term memory in that pink there to working memory in the purple, for example, we have to transition from this kind of transient, not being able to do with it kind of storage to actually performing a manipulation with that information. So what do I mean by manipulation? So imagine you have, just pretend for a moment that you have this really enormous family, you're at a family reunion and you've learned several new names. So to use working memory in this context, you would have to pull those new names from short-term memory and then actively try to understand their relationship to each other. So now you're manipulating the family relationships in your mind to understand, you know, who's the second cousin, who's 3 times removed from who, and so on. So that's one example of working memory. You know, I pulled the names that I heard from short-term memory. Now I'm actively trying to manipulate, dynamically visualize them and their relationships in some way. You know, another really common example of working memory is doing math problems in your head. So maybe you're at a restaurant and you're trying to calculate the tip, or maybe you're trying to add, subtract, multiply, or divide different numbers. All of these kinds of manipulations or computations that we carry out in our head fall under the umbrella of working memory. Now, long-term memory is often what we refer to when we talk about memory, right? So when people say my memory is so bad or my memory is so good, they're usually referring to long-term storage. And this is really the ability to remember things that happened weeks ago, months ago, years ago. It's often episodically structured or event structured so that you can remember something that happened on an important birthday or things that happened in the news that were salient. And in order to bring something into long-term memory, as you can see from the schematic, it requires additional processes to transition from short-term memory to something that you can hold on to for a long time. And we call that process consolidation, and you can see it in orange here. So I've learned a number of new names, for example, and now I'm going to consolidate that information into long-term memory so that I can say hi to all these new people at our next family reunion. And then finally, if I were to ask you to describe your most memorable reunion and also described who was there and how each of those people were related, that would be an example of retrieving something from long-term memory and pulling it into working memory. So understanding these core kinds of memory and how we can move through them has really been the focus of careers of thousands of scientists. And because of the complexity of the brain, each of the components in this little picture is actually a billion-piece puzzle. And so I'm just going to walk through a few of those pieces and share some examples of the types of research that's been done to understand which brain regions and in processes enable these different forms of memory. Now, this is one of my favorite memory studies. It's a really seminal discovery from the 70s, and they identified what is called a memory cell. And so what are memory cells? So if you record a single brain cell in the brain, literally the activity of one single neuron, you can see its activity or its firing rate, and you can quantify how active it is over time. And the discovery of memory cells really reflected the finding that some cells in the brain increase their activity when you're actively trying to remember something. So if you cue this monkey that you see here on the left and show it where some food is, right now that food is being shown in the well that's on its right. And then you occlude its view with this divider. And several seconds later, you lift the divider and let the monkey make a choice of whether they're going to uncover the well on their right or their left. What you'll see is that some cells in the brain actually show an increase in activity during that period when that divider was actually down, when the monkey couldn't see anything. So those are the cells holding on to the memory that food was in the right well. So this kind of cell is activated not by the sensory event itself, not by the sight of the food, but by the retention interval linking the sensory event to an adaptive response. So this finding really spurred thousands of follow-up studies to kind of disentangle the different regions of the brain that showed this behavior and what kinds of stimuli and what kinds of delay or retention intervals and so on were able to elicit this kind of activity. And also under what conditions these kinds of memory cells fail. And one of the big conclusions is that these kinds of memory cells, to a greater or less extent, are found in many regions throughout the brain, cortical and subcortical. And here are just some examples illustrating really the diversity of activity patterns of individual brain cells trying to remember things. So each row reflects a different kind of brain cell. Some cells increase their activity or firing rate, as you can see in red, for a short period of time when the divider goes down and up, like in row A. Some cells actually reduce their activity levels during the delay, like in row I. And some cells have a high level activity or firing rate throughout the delay period, like in rows C and D. So they're actively trying to hold onto the memory by sustaining their firing rate when the thing that they're trying to remember is no longer in front of them. And there have been quite a lot of studies showing this kind of behavior in humans too. So in this case, using fMRI activation instead of the activity of single neurons, since those recordings are too invasive for humans. But suffice it to say that the different patterns of memory cells we see in animals, so higher activity during the retention interval when the thing you're trying to remember has been removed from sight, is also something that happens in humans. So here you'll notice our original diagram on the left. And what we've highlighted is that these kinds of memory cells are thought to heavily support working memory and short-term memory. And on the right is a revised diagram from a review paper that was published 30 years after this initial discovery of memory cells. And it summarizes the circuit architecture underlying working memory and short-term memory. And this is really just to showcase the extensive complexity in research that has gone into understanding the flow of information involved in just being able to remember things for a short period of time and to be able to manipulate them. And this newer architecture really supports the idea that the whole brain is involved in memory. So there are many different kinds of memory and different brain regions that specialize in those different kinds of memory. So this is demonstrated by a set of really beautiful studies looking at memory in rodents. And what you'll see on this slide and the ones that follow is that if you damage specific regions of the brain, then you can impair some forms of memory, but not others. So the others will remain intact even when you have specific forms of brain damage. So in this first example, the rat needs to learn a memory task where food is located at a specific spatial location somewhere in the maze that you see on the left. And if you cut or damage the hippocampus of that rat, but not other regions of the brain, the animals are severely impaired at doing this task well. So in that graph on the right, you can see that that blue line reflecting the performance after damage to their hippocampus is much lower than the other lines where there was damage to other areas of the brain. So what that tells us is that the hippocampus is important for spatial memory, remembering where things are in space. So for example, where your fridge is located in your house. Now, another form of memory is remembering how to move relative to one's own body. So in this task, a specific spatial location isn't rewarded like on the previous slide. Instead, a type of movement relative to the animal's own position is rewarded. So what I mean by example is if the animal turns right instead of left, wherever they are placed in the box, then they get the reward. And in this case, damage to the caudate nucleus impairs this form of memory. But as you can see, memory is intact when there's damage to other regions. So the purple line is at the bottom now, but the blue line representing damage to the hippocampus from the previous slide is doing just fine. It's high up. Now, if the type of memory involved requires visual recognition, so memory for an object instead of a location in space, then damaging the visual cortex will impair memory now. So now the red line is the worst, but purple and blue are high up and doing just fine. So these are just examples of 3 different kinds of memory and 3 different brain regions supporting each of them. Now, moving on to long-term memory, you'll find that this is a very, very big category that has many subdivisions that are worth considering individually because they really reflect the activation of constellations of different brain areas. But within long-term memory, the most important distinction is between declarative and non-declarative memory. And declarative memory are things like memory for events that happen in your life, the ability to name the capitals of the United States, to be able to recite the alphabet, for example. And the non-declarative memory are things like your memory for how to ride a bicycle. And arguably the form of memory that we talk about the most in everyday life, with our friends, our colleagues, our family members, our acquaintances, is episodic memory. So you'll see that one under the declarative section. And these are things that we remembered that happened in our life, historically significant events, things that are more autobiographical in nature. And this is one of the more obvious symptoms in Alzheimer's disease and related dementias, where patients notice that they're having trouble recalling things that happened the day before, the week before. And family members are starting to notice that there are massive failures in episodic memory specifically. So a great deal of effort has gone into understanding which brain regions are especially important for episodic memory and why they're selectively impaired in the early stages of Alzheimer's disease. And one answer to that question came from really the most famous neurological patient in history. And you're looking at a picture of him here. His name is HM, or Henry is his first name. And what made Henry such an important case is that he underwent neurological surgery to treat epilepsy. So he was having seizures. And they localized the seizure activity to a place in the brain called the medial temporal lobe, which includes the rhinal cortex and the hippocampus. And to eliminate the seizures, they removed parts of these brain structures on both sides of his brain. And the great news is that his epilepsy was more or less cured. He didn't suffer from constant seizures all day thereafter. But the bad news is that he couldn't remember any new events in his life that happened after the surgery. And he also lost a significant amount of episodic memory of his life from before the surgery. So he was essentially trapped in the present. So just as one example, he had seen a nurse that he had worked with for the past 20 years, and he would have to ask her what her name was at each visit. So just trapped in the eternal now was HM's lived experience. Now, even though he was unable to form new declarative or episodic memories of life events due to damage to the medial temporal lobe in order to cure his epilepsy, he was still able to learn new types of non-declarative memory. So remember, that's more like riding a bicycle, motor memory type processes, because the medial temporal lobe doesn't support those non-declarative forms of memory as much. So in this famous study, he learned how to trace a star in a mirror. It's actually a really hard task to do at first, but after you practice 10 or 20 times, you can get quite good at it. And you can see Henry's performance on this mirror tracing task at the bottom. He was actually able to get really good at it on his 3rd day of practice, which is shown by that very flat red line indicating no errors on the task. But when people asked him to do this task after he was already proficient at doing it, he was completely surprised that he could even do it in the first place because he had no episodic memory of actually learning the task. So this is a really nice dissociation between these different forms of memory, declarative versus non-declarative. His declarative memory was damaged, so he couldn't remember that he had spent the time learning this task, but his non-declarative memory was still preserved, it was still intact, and his body was able to carry out the task really well. So why are these forms of declarative memory also compromised in Alzheimer's disease? So as you can imagine, a great deal of effort has gone into understanding really the neurological basis of dementia. And one of the insights, at least, is that ground zero for Alzheimer's is the medial temporal lobe, so specifically the entorhinal cortex. And that's where the observable pathology sort of hits first and then spreads elsewhere. So in early AD or Alzheimer's, people show impairments in declarative episodic memory, since the brain regions affected first by the pathology support those forms of memory. But then down the road, everything goes offline eventually, and the loss of cognitive function really mirrors the disease spreading throughout the brain from the mediotemporal lobe to other regions. But what many find striking about memory in the context of dementia is that the regions supporting music is affected quite a bit less and quite a bit later than the regions supporting episodic memory. So this is why some patients with dementia can't remember the name of an important family member, but they can still sing or hum a tune from, their favorite song from their childhood. So musical memories are actually really quite special. They're preserved for longer. They're more robust to atrophy. They have lower levels of destruction than the structures that support other forms of memory, specifically episodic declarative memory forms. Now, in the healthy brain, why do we remember some events better than others? Everybody can remember where they were, for example, with the JFK assassinations or where they were with the 9/11 attacks. So the question becomes, what makes some memories more likely to be consolidated into long-term memory over others? And one of the big answers here is emotional arousal facilitates consolidation, for better or for worse. So when there is an emotional component to an episode or a life experience, it activates an additional set of neurocircuitry that's involved in the stress response and emotional arousal more generally. And this emotion circuit is heavily interconnected with brain regions that support memory. So a lot of work has gone into understanding how the hormones and neurotransmitters involved in emotional arousal and stress interact with memory structures in the brain to improve consolidation of memory, right? Moving from short-term memory over onto long-term memory. But on the flip side, there are conditions such as PTSD comes to mind, which have been proposed to really reflect too much emotional modulation of memory that promotes consolidation of events that we would rather forget. All right, so we've learned that the emotional strength of an event can cause differences in how much or how well we can remember things. But there are also structural, chemical, functional, brain-based differences across individuals that can strongly influence consolidation. And there is a great deal of neurodiversity out there in the world, and these neurodivergent brains are sometimes able to carry out some really amazing feats in terms of memory. So in the movie that many of you may have seen called Rain Man with Dustin Hoffman, it was based on this gentleman that you see on the left. His name is Kim Peek. He was able to memorize books and dates with just incredible accuracy. So for any date he was given, he could report things that happened on that day. He could also read books and remember which words appeared on which pages in that book. And then this gentleman you see on the upper right, he was able to absorb essentially all of the visual information required to reproduce a sketch of the New York City skyline with just a single 20-minute helicopter ride. So he got in the helicopter for 20 minutes. He looked at the New York skyline and he produced the sketch that you see here quite accurately. So I couldn't do that. Most people couldn't do that, but he certainly could. And this might seem like a blessing, and in some ways it can be, but in many cases, exceptional memory like this comes at a cost. So for example, Kim Peek was never able to live independently, and Jill Price, who you see on the right, she remembered every autobiographical detail and date really to her detriment because she couldn't let go of painful memories or even irrelevant details that she preferred to forget. So in some cases, the inability to forget information actually interferes with normal functioning. So what makes these people the way they are? We know that every brain is different, but in several of these cases, the volume of certain brain regions differed from those with typical memory capacities. They may have enhanced functional connectivity between regions. They may have higher concentrations of neurotransmitters and hormones involved in attention, memory, and learning. Various other theories, of course, have been proposed as well. So it's an active area of research, but it's, of course, going to be limited by the number of participants with these exceptional memories that are available. It might surprise you, however, to know that some people who show evidence of exceptional memory are not all that unique in brain structure or function, though. So one example are people who use memory techniques to accomplish some pretty impressive memory feats. And so the guy you're seeing here, this is an example of a reporter. He wrote a book on memory and in the process of doing so became fluent in with memory techniques to memorize arbitrary things like the digits of pi or the order, the exact sequential order of a deck of cards. And it became kind of like a hobby of his that he pursued by practicing regularly. And near the end of the book, he talks about how he entered the USA memory competition and he miraculously won first place there. So most people are able to practice these memory techniques to increase their capacity by quite a bit. And if you want to practice one of these memory techniques yourself, then I suggest starting with the method of loci, is what this is called. And in this approach, what you're going to do is you're going to develop a very strong, detailed mental image of a certain place. So perhaps your childhood home in this example, or another favorite spot. And then you have to develop a very careful path of visual imagery that guides you through that entire place. So in this case, the first location in this house starts with a picture near the stairs. You'll see the one by the stairs over there highlighted in orange. And then it goes through the entire house step by step with 52 specific locations. And once you've been able to establish these ordered locations, in your mind, then you're going to be able to use them to remember more things. So this memory palace has 52 locations because the person who developed it really wanted to use it for memorizing an entire deck of cards in order. And this is how they did it. The person looks at each card once as it's flipped, and then they're going to use visual imagery and emotional impact to put the card in its corresponding location in their memory palace. So for example, if the very first card that's flipped over is a 7 of hearts, then you're going to imagine in your head and remember the 7 at the 7 of hearts at spot 1 at the foot of the stairs by imagining that the 7 and the heart are interacting with the steps in some emotionally charged way. Because remember, the emotion helps consolidate the memory. And if the next card is the Queen of Diamonds, then you're going to imagine or remember the Queen of Diamonds at spot 2 in some emotionally charged way. And you go on so forth until you have one card associated with each of the 52 locations in your memory palace. Then when it comes time to recall the cards, you're just going to walk through your memory palace in your head, starting at location 1 in order and ending at location 52. And through those emotional associations, you'll be able to pretty easily recall those 52 cards in order. That said, these types of memory techniques are actually compensatory strategies to improving memory. From a neurological perspective, you're working around the issue rather than addressing it directly. So if you think about memory loss as really the failure of brain cells to do what they're supposed to do. So for example, retain their fine rate during the retention interval when that divider was down in the case of that monkey, then anything that promotes the health of those individual brain cells is going to promote better memory ability. And neuroplasticity researchers have really shown that one of the best ways to improve your brain health is to train your brain and improve how well it can process information. So if you improve the speed and accuracy of information processing, that will improve the fidelity of the representation feeding into memory structures to improve your cognitive function, which will then in turn translate into how well you're able to carry out your responsibilities in daily life. And this framework to brain health is supported by one of the largest multi-site double-blind studies in brain training to date called the IMPACT trial. And in this trial, 400 participants were randomized either to BrainHQ or in green or to an active control program of just watching educational programs. And what they found is that even though the BrainHQ training in the study focused on the speed and accuracy of information processing, the training led to improvements in memory function on independent memory tests. And then that generalized to patient reported outcomes of cognition in their everyday life. So brain training that improves the speed and accuracy of information processing has been found to improve all these various measures that kind of go haywire in an older brain, and it restores them to a more youthful status. So it can reduce neuronal noisiness. It can improve processing over space and time so that you can correctly encode the information coming in from your senses. And if things are correctly coded, your brain will have a much easier time being able to remember them. So what I think is the most helpful analogy for me is to think about the game of telephone that you may have played with your friends when you were younger. So this is the game where people take turns whispering a message into the ear of the next person. And then eventually the person at the end of the line will say the message out loud. It's usually really funny because it bears no resemblance to their original message. And I really like this analogy when we talk about brain health because it demonstrates that if the initial incoming message is whispered and unclear, then the message will become increasingly distorted as it passes down the line. So the brain can't remember a sensory event when it doesn't process that sensory event well. Now, in contrast, if the incoming message is really loud and clear, there's less ambiguity, less distortion, and the original message is more likely to be retained. So slow and noisy representations at the start of the processing chain can lead to more distorted memories, and clear representations and good brain health of individual cells can lead to more accurate memories. So Mike, I know that I cited a lot of your work from this side specifically. People usually have a lot of questions about memory. What do you think about moving on to the discussion portion of this webinar?
Well, you certainly was a wonderful introduction. I love it.
Well, so, you know, you're a neuroscientist and you've lived through very, very many breakthroughs in the science of memory. What are some of your favorite breakthroughs in understanding?
Well, there are almost too many to count because you know, there's been so much greater development of understanding of memory processes since I initiated my work as a brain scientist. It's been a wonderful evolution and with increased understanding. But just to highlight a few things. You talked about the research of Patricia Goldman-Rakic. And she was a great Yale professor, a friend of mine historically. And she actually brilliantly described the processes that control sustained or working memory. And basically, she saw that cells in certain regions of the brain reverberated in their activity. They sustained their activity across a period of 1 to 2 minutes, as a rule, when you were in a memory operation that was important for you from the point of view of making memory associations to the other things that might relate to what just happened. And so we understand the nature of this reverberation, and then researchers that collaborated with her or who were inspired by her began to try to study the processes in parallel with what she was doing to understand what it took to generate and sustain that reverberation. And it takes two things, main things. It takes a strong level of activity in the processes that control emotion and that control plasticity itself. And it takes very highly coordinated information feeding these areas of the brain. Now, why is this so important? Because basically our memories are based upon associating what happens from the moment to the next, this moment to the next moment. And it's all dependent on sustaining what we're operating on in time. And so basically being able to hold things in memory and time and basically as a setup for associating things. What a wonderful, insightful discovery this was. And about the same period, Japanese scientists conducted what I think is one of the most exciting studies. I think it should have led to the awarding of a Nobel Prize. And what they did was they studied in monkeys. We can argue about the appropriateness of doing experiments in monkeys, but in monkeys, they did these beautiful studies in which they trained monkeys to remember sequences of things that would normally not be seen to belong together. So let's say that I expose a monkey to an apple and then a hammer. And so the monkey, basically what they saw before long was that it was very easy to go into the brain of the monkey and find brain cells that responded only to hammers. Could not find anything else they responded to. And they were commonly associated, localized next to cells that only responded what did I say, apples? To apples. So I have apples next to hammers. And then they're recording from these cells while the monkey is not in the task anymore. And suddenly the hammer cell starts to respond. And then in the next moment, the apple cells start to respond. Or maybe it goes in reverse. The apple cells start to respond, and then the hammer cells respond. So they have a special relationship. That's another way of saying hammers predict apples, apples predict hammers. And that's the essence. You could call that the motor that controls the speed of consciousness, the stream of consciousness. So we move from moment to moment, always forward predicting based upon our memory, based upon the things in a pad that associated. And that's what basically is the basis of the organization of our thoughts, of the organization of the flow of our understandings of things. They all are mounted in the domain, in domains of space and time, all driven by the things we associate across time, all coming from our memories. What a wonderful gift this is. So I could cite 50 other things, but these are two of my favorite things from two sets of my favorite scientists.
Mm-hmm. And when we think about the brain being a plastic organ, we kind of recognize that it can change plastically for the better. You know, as you mentioned, minutes, hours, days, over weeks, but it can also change plastically for the worse on those exact same time scales.
Right.
So
Right.
what are common things that we're doing in our daily lives? So for example, on a typical day, just like today, that's actually hurting our ability to remember things.
Well, that's a wonderful question. First, I want to say that life is full of vicissitudes. We all have struggles, and maybe those struggles have been, and commonly there are things we can't avoid. Maybe we drink too much. Maybe we've used drugs. Maybe we have a life of continuous stress, or maybe we have a period of life that's particularly stressful. Something happens to us that's particularly stressful to us. And basically it degrades our operations and basically slows down and reduces the accuracy of the operations of our brain in ways that will impact our memory, both the remembering of new things and the recollection, the processing of information that's coming from our memory stores. Everything represented in a noisier form, in a less precise form. And therefore, it's all impaired by this. So, of course, when you have a vicissitude, you identify such a problem, you need to address it. You need to exercise your brain. You need to change your life. You need to get out there in a way that provides the kind of exercise your brain is demanding to restore your abilities, to strengthen them, not to let them slide further, and hopefully to regain abilities that you applied for your more useful life. That's one thing. The second thing you can do, people commonly do, is they just give up on engaging the machinery that keeps their brain spirited, alive, emotionally engaged in new things in ways that the machinery that controls its plasticity, because it's all about plasticity. When you see something and remember it, there have been plastic changes in your brain, and they're absolutely dependent upon the machinery that controls plasticity, that supports it. So you need to keep that machinery in good health. Mm-hmm. And that demands an active life in which you're using your brain in a continually challenging way to accomplish new things in life. Mm-hmm. I'll say one last thing. Why stop loading the encyclopedia? Why give up on continuously adding to your memory storage, to the information you have in there that you can retrieve across all domains? Because one of the most important things about recovering a memory is to use all of the dimensions of how you might find that name or come to that understanding from your memory stores. And those come from what you've seen, what you've heard. It comes from how it's been written. It comes from all of the dimensions of your senses that might give you the important clues, important information that will guide you to coming up with that name or that answer or that understanding. And so you want to keep all of those things in good shape, and you want to continue to enrich them, of course.
Mm-hmm. It reminds me of how we're sort of constantly outsourcing our memory, right? We outsource it to our phone and to our apps and to pen and paper, right? So we use GPS really at the detriment of our spatial memory. We use calculators to do math on our behalf at the detriment of our working memory, right? We write these really long, extensive to-do lists at the expense of our long-term memory. And really over time, that constant outsourcing downregulates those memory networks, and it makes them harder to do on your own, right? So you can get a healthier brain just by minimizing those external memory strategies, because, right, your brain is use it or lose it.
Mouna, you're so smart, and you always, almost every time I talk to you, you make me remember that I could have should be almost at the top of my list. You know, basically we look up the answer to everything.
Yeah.
We don't dwell, we don't exercise the machinery of recollection. We do all kinds of things. It's as if we can live life successfully without very much use of our brain. And all of the practice we don't have, that we don't get. It's an incredible weakness, you could say, that's contributed to us from our technological lives.
Mm-hmm. And so what is your all-time favorite brain healthy activity?
Well,
if you had to name one concrete activity, what would it be?
You mean to improve my memory?
Yeah, just something you do in daily life that's a healthy activity that you really enjoy.
Well, let me just say, just first of all, I do the New York Times crossword puzzle every day. I have for 50 years. But I'm not so foolish as to believe I'm going to improve my memory by doing that.
You just enjoy it.
I just enjoy it. And in fact, as you know, in many studies using BrainHQ, it's been used. puzzle solving like this has been used as a control task,
Mhm.
because people do believe it's so good for their memory. And it's not that it's not a positive thing to do, but it's not really very effectively going to change anything, right?
Mhm.
So, I mean, let's put it another way. BrainHQ always wins.
Mhm.
And that's why it's used as a control task. But to make a long story short, I just try to continually engage my brain in a schedule of new learning. And by new learning, I mean to acquire new ability, to acquire new information at something I don't understand, to elaborate my brain operations in an aggressive way. I'm trying my damnedest to sustain my brain health as long and as effectively as I can. And I do that in all kinds of ways. I mean, it's in the variety of ways that I can keep myself vigorous and alive.
Mhm.
Right now, it's in making Christmas presents, which I do every year for all my
That you're making though.
yeah. So I'm busy in that. I always try to do something that's unexpected for the receivers, and
Mhm.
that requires new skill for me. And
New skill set.
so I do things like this all the time because I know it's good for me to keep my brain alive and vigorous.
Mhm.
And that's a main thing that I'm trying to do. And I mean, I'm an extremely avid reader.
That's true. You really are. Mhm. So Stephanie, I have like a ton more questions for you, but should we let the audience ask some of their own questions?
Yeah, absolutely. So we had a couple of questions come in, I think from one of the first two slides that you had in your presentation, where you were talking about olfactory and how like smell can have an effect on your memory. People wanted to know if taste was also a part of that experience, like if having a childhood food is going to bring you back to a memory from your childhood, for example. Is that a thing that can happen, and why does that happen, if so?
Of course, we associate all kinds of things. You think of, I have an apple in my hand. And first of all, I identify it as an apple because all of the things that represent appleness go with it. And one of those things is its smell, and one of those things is its taste. And in 100 ways, I can be reminded of the apple. I can go from the smell of the apple pie to the apple. I can go from the smell of the orchard to the apple. In all kinds of ways, I can get to the apple through these associations in memory. So I have a rich ability to come up to the 101 things that represent appleness, through using all of my senses. And I continually, it's human, it's our big human strength, our power, our secret power, is that we have more ways to reference our memory stores than any other creature, primarily contributed in extension to two things. The first and primary thing is language. We have developed a language, and we don't just speak it. It's presented to us in written form. And then there are all kinds of graphical representations of those things that are written about or that are spoken about. And our second way we have an advantage over almost every other creature on the planet is this. We're able to make things. We're able to manipulate things in ways almost no one else is able to manipulate them. And we have all of those things constantly providing us the basis of coming to the answer. It's the secret of the Google search engine. The more ways you can basically come to the answer, the more certain you are of it and the easier it is for you to find it. So too with your memory. So keep all of those things alive and healthy and active and effective, and you're going to be a lot better at remembering what's happened and what is happening.
All right, thanks, Mike. We had a couple of people ask about word finding. When you're having a conversation and you're forgetting words, why do we sometimes forget specific words? And are there things like maybe in BrainHQ that we can recommend to help with word finding?
Mouna, this one's for you.
Yeah, there's something called tip of the tongue phenomenon where you feel like the word is right there, but you can't quite retrieve it. So if we go to that memory schematic, it was the retrieval part from taking something out of long-term memory and putting it into working memory. And as we age, those areas are kind of they struggle a bit more if we aren't really practicing our retrieval skills. But if you can practice your retrieval, so what comes to mind are, the exercises like syllable stacks and to-do list training, and maybe even juggle factor. If we can do a better job retrieving information and practicing that, we can actually improve those structures to recall words faster in conversation. But that is an example of just slower speed of processing as we age. And a lot of people experience it, but there's something that can be done about it as well.
Yeah, improving the speed and accuracy of how the brain represents information of what you're trying to remember and whatever you're trying to remember. And remember in all of its forms. Again, it can be the word that represents the thing, or it can be an image of the thing, or it can be in all kinds of ways we might bear reference to our coming to remembering what the thing is, what the answer is. And so we want to keep all of those things in good shape by improving and sustaining their accuracy and speed of how we represent them in detail in our brains. That's called brain health. No, it's not magic. Healthy brain is the key.
All right. So another question, this might end up being our last question because we are a little bit pressed for time here. But there have been quite a few people who have written in and said, I have trouble remembering faces and names, which can be embarrassing, or, other circumstances where like somebody will read a paragraph and then realize by the end of the paragraph they didn't actually take any information in. Is that a memory problem, or is that more of a speed of processing and attention problem? And how do those things kind of relate?
Yes.
Yes, to
Yeah.
all of the above.
To my mind, Mouna, I would say that it relates to the fidelity with which you're representing information in your brain.
Just like the penny activity, it's not just about looking at it. You have to form the associations in a meaningful way with the name and the face, for example, to remember it.
Yeah, and you have to represent those things in clarity, with salience. And that means to say you need a sharp representation, which means you need to engage your brain to sharpen its operations, sharpen them in time, sharpen them in place, sharpening them in detail. And that's what BrainHQ is largely designed to do. It's designed to re-refine the representation of information in your brain. So the brain is again operating with highly resolved processing of it or treatment of information, not just information that's just been received or is being received, but also in information that's hanging around in there that you're trying to retrieve. You want to represent everything with greater saliency, with greater clarity. And that's what a healthy brain does. It represents information in a clearer form, in a sharper form. That's what you need to do again. You need to try to get back there. And you need to work to do that. It's not free. Just like physical exercise.
Yeah. And you also need attention to be able to remember things. So if your eyes were just kind of going left to right, up to down on the lines of a book, you're not going to retain anything because you weren't paying attention. You were actually thinking about something else entirely. So yes, of course, you're not going to remember that paragraph. You have to revisit it. So improving your attention and focusing will also improve your memory. But memory requires attention.
That's another way of saying, Mouna, as you know, that it's so dependent upon having strong chemical control machinery in the brain that you use basically to support its plastic recovery. And many people struggle with that at an older age because basically they haven't exercised it enough.
Yeah.
And one of the things we try to do in BrainHQ is to strengthen it again so that it's operating like the brain as it is in a younger person. So that basically the capacity to change in that improving or recovering direction and the basic, it's so critical for memory itself because you remember better, not things that you not just attend to, but things that in general really matter to you, that are important to you, that are rewarding to you, that are naturally rewarded to you. Because when you come up with a name, that person, it's positively rewarding, of course.
That's true. That's true.
All right, so we are a minute past the hour, so unfortunately, I'm going to have to probably call it there. Thank you, everybody who sent in your questions. I'm so sorry that we weren't able to get to all of them, but I will hang back in the webinar and answer any just general BrainHQ support questions that I can. Let's go ahead and pivot to our end screen here. Give me just a second. Once again, thank you all so much for participating in the webinar today. Mouna and Mike, thank you so much for presenting and also the wonderful discussion and answering our audience members' questions. It's always delightful to have you both on webinars, and I really want to thank you for your time today and joining us and doing that for us.
Thanks. Appreciate it. Yeah, I hope
Yeah.
what everyone has learned is that there's just no one portion of the brain responsible for all of memory. The brain itself is really this memory machine, and you can always improve that machinery, right? So you can become a memory champion using those compensatory strategies, but you could, better yet, you would improve your memory really from the bottom up by improving your brain health and engaging in activities that just improve the speed and accuracy of what you see and hear and touch.
Well, maybe, Mouna, you could do both. Just for the
Yeah, you can do both. I have done the method of loci, and it's really a lot of fun. It's a fun party trick.
Well, that is a wonderful message to leave off on. So thank you, everybody, once again. For those of you who are interested in our next webinar, on January 15th, we're having an office hours webinar about how to set your schedule and training goals. This is a repeat webinar, but maybe some of you are going to have a New Year's resolution about training more in the new year, and so we're here to help with that. So invitations for that webinar will go out a week beforehand. I think we've already had sort of final words, so I'll thank everybody once again, and I hope you all have a wonderful rest of your day and happy brain training.